Yep, that's right. We're here. What's the point of being able to do calculus? Eh, to begin with, you can optimize situations. In other words, find the biggest or the smallest or the best or the least expensive. Um, Most of you guys are studying business. Some of you are studying biology, or you're going to go to pharmacy school or something like that. But in all of those fields, finding the best way to do something is absolutely necessary. So I'm just going to give you some examples here. What I want you to watch for in the problems are the words maximize and minimize. When you see those words, you have to look at what they're asking you to maximize or minimize. Are you maximizing the volume or the area? Are you minimizing the surface area or the cost? It's always important to know what it is that you're maximizing or minimizing, because that's the formula that you have to come up with. Okay? So, example one, these are classic problems. A farmer has, let's say, 360 feet of fencing to enclose a rectangular area the barn will be one side, fencing on the other three sides. You're also going to have to draw on some things that you already know, like the area of a rectangle in this case. Maximize the area. So what do you have to find the formula for? Area of a rectangle. Well, area is length times width. Okay? So you know the formula, but now you got to know the situation. So we're going to say, here's the barn. Always draw a picture if you can. We're going to enclose a rectangular area next to the barn. So these sides here are fencing. And if you want to maximize the area, then you want to use all of the fence. And there's 360 feet. So we need to figure out what's the length and what's the width. Well, if you don't know something, you usually call it X, right? And we see that because this is a rectangle, okay, pretend it's actually straight. Because it's a rectangle, this side and this side are equal to each other. And most of you at this very second are thinking this is Y. All right, well, we can't have a combination of X and Y. We can only have X's. So we have to think about the situation here. We've got 360 feet of fencing. Well, how much have we already used? We know this is X and we know this is X. So this is all of the fencing that we have minus what we've already used. This is the rest. So that will be the total amount of fencing minus the two X's that we've used so far. So what is the area enclosed? One side is X, the other is 360 minus 2X. There's the formula for the area that you want to maximize. So how did we find maximums and minimums when we were graphing? We found the critical values. So what we want to do is simplify this thing, take the derivative, set it equal to 0, solve for X, and boom, you're done. So the area is 360X minus 2x squared. Take the derivative, we get 360 minus 4x. Set that equal to 0. X equals 360 divided by 4. I get 90 feet of fencing. That's inches. Haha, 90 feet of fencing. So what's the area of the enclosed space? It'll be 90 feet on one side and 360 minus 90 twice. What is 360 minus 2 90s? 180. So you want to find the area, the maximum area of this enclosed space. All right, let's try another one. All right, let's say we have a piece of cardboard or tin or aluminum or something, and we want to cut squares out of the corners. These are perfect squares. They're all the same size. And when we cut those corners out, think about what we have left. I'm going to do a little erasing here so we can see this. If we cut these corners out, do you see that we have flaps? If we fold those flaps up along the blue dotted line here, fold up those flaps, and you'll see that we make, okay, my hand got in the way here. When we fold up the flaps, we can make a box. Oh, I'm doing such a good job. Look at that. So we want to maximize the volume of the box. Whatever material it is. And our sheet was originally, let's say 20 inches by 14 inches. Made by cutting out squares from the corners. You'll see this problem in your homework, and they write it much better than I do. But my picture is excellent. What size squares should be cut out to maximize the volume? Okay, so here's the deal. We originally had a piece of cardboard that was 20 inches one way and 14 inches the other. But then we cut out these squares that are X by X. Squares, so they're the same length on both sides. And we cut that out of each of the corners. So when you see the finished box, this side was 20 inches, but we cut out from each end. Do you see that? We had 20 inches, but we cut out X here and X here. So we end up with 20, take away the two X's. And this side is 14 minus the two corners. How deep is the box? Because volume is length times width times height. We need to know the height of the box. Well, each of those flaps was X inches. So that's the height of the box. So my volume is X by 20 minus 2 X's by 14 minus 2 X's. Do you see it? So what do you do? What are you supposed to maximize? You're maximizing volume. And you're solving for the size of the squares, which would be X. So if you're told to maximize something, you find the formula, you take the derivative, set it equal to 0, get the values of X. Now in this case, you're going to get two different values of X. One will make sense and the other one won't. So you'll know which one is the right answer. I'm going to FOIL this out. 14 times 20 is 280. And then the outer's 40 and the inner's 28 gives me minus 68x. And then 2 times 2, a minus times a minus, x times x. Now distribute that x, and I'm going to write the highest power first, if you don't mind. And there we have the formula for the volume. So to maximize, you take the derivative. 12x squared minus 136x plus 280. Set that equal to 0. Solve for x. I can pull out a 4. You can always pull out a 4 from these problems. Now this guy doesn't factor, so I'm going to use the quadratic formula. By the way, this 4 that we factored out, that's a factor, right? And it can't equal 0, so I can just blow him off. And just factor what's in the parentheses. So negative b plus or minus the square root of b squared minus 4ac. The whole thing is over 2a. I'm going to get the square root of 316 over 6. Now, when I plug that in my calculator and I chug out the answers, I'm going to get 8.63 ... inches. These are approximate. Or 2.7 something inches. Two answers. How do I figure out which answer is the right answer? Think about what you're doing. You had a piece of cardboard that was 20 by 14, and you cut out squares from the corners. Each of these squares, if each of them was 8 inches, that's 8 inches, 8.6 inches here and 8.6 inches here. I'd be taking away, 17 point something inches? I can't do that from 14. So the 8 doesn't make any sense. That means my squares are 2.7 inches by 2.7 inches. So one of the answers makes sense and the other one doesn't. Okay, one more example. I'm going to make a can for soup or stew or something like that. All right. So the can has two dimensions that we know of, that we use. It has a radius and a height. Okay. So I want the volume of my can. I know how much product I want to put in the can. Let's say I need 48 cubic inches of product inside the can, but I have to pay for the packaging. I need to minimize the cost of packaging, so I want to minimize the amount of materials that go into the packaging. Well, what is the packaging? It's the surface area of the can. So I want to minimize the surface area of the can and find the dimensions of the minimum surface area. Okay, a can is a cylinder. We know that the volume of a cylinder, or do we know? Think about what a cylinder is. I'm going to draw something and then erase it. A cylinder is a circle with height, right? Well, the area of the circle is pi r squared. And I've got circles stacked on top of circles, stacked on top of circles, until I have a solid. And that height is my third dimension. So the volume of a volume of a cylinder is the area of the circle with height. Simple enough. What about surface area? Think about what the surface area is. You have a top and a bottom. They're both circles. What's the area of a circle? Pi r squared. They're both the same, so you have two of them. But what about the sides of the can? Again, I'm going to draw something. If I take the label off of a soup can and lay it down on the table, it's just a rectangle, right? And it has the height of the can. But what about this dimension here? What is this? Well, think about it. It wrapped around the can. So that is the circumference of the circle to pi r. So that gives me my outside surface area, 2 pi r h. So the surface area of a cylinder is the top and the bottom plus the outside. What I want to do is I know the volume has to be 48. Here's the formula for that. This is the constraint that I have to keep while working the problem. But this is what I want to minimize. I want to take the derivative of this. I have an issue though. There's an h in there. I can't take the derivative of it with two different variables. So I don't want to get rid of the r. That's in two different places. I want to get rid of the h. And the way I do that is I use this right here. If I know the volume is 48 and volume is pi r squared h, I can solve for h. So let's do that over here. So the pi r squared h is the volume, 48. That makes h 48 divided by pi r squared. And now I can take this and stick it right here for that h, and the only thing left in my question is r. So surface area is 2 pi r squared plus 2 pi r h. Simplifying that piece, I have a 2 times 48, which gives me 96. The pi's cancel. and this r cancels one of those r's, and I end up with an r in the denominator. Now when I take the derivative of this piece, I'm going to see this as 96 r to the minus 1. Let's make a little note over here on the side. I have 96 over r equals 96 r to the minus 1. So the derivative of this thing is going to be a minus and r to the minus 2. So you see when you take the derivative of a constant divided by the variable, it's just change the sign and square the bottom. All right, so that's what we're going to do when we take this derivative here. So we're minimizing the surface area. So the first bit here gives me 4 pi r minus 96 over r squared. We're going to set that equal to 0, get a common denominator, and now you've heard me preach enough in the last few videos about setting a rational function equal to 0. Only the top can make it equal 0. So this is the only thing I have to worry about. The radius is never going to be 0. So I'm going to get 4 pi r cubed equals 96. I'm going to divide both sides by 4 pi. R cubed is going to be 96 divided by 4 is 24 over pi. And my r is going to be the cube root of all of that stuff. It's just a number. Stick it in your calculator and figure out what it is. And I get 1.969 ... inches. So I'm going to use 2 inches. Remember, that's the radius of the can. So if the radius is 2, then the height is this. 48 divided by 4 is 12. 12 over pi is going to be right around 4 inches. Now, I didn't even calculate that because 4 is close enough. When you're looking for the most optimal situation, you're going to get something that's as close as possible to a sphere or a cube or a square or a circle. So we got the radius of this thing was right around 2, and the height is 4. So if the radius is 2, then the diameter is 4, and that gives you the maximum volume with the minimum surface area. Okay, so we guesstimated a little bit with the radius. We made it a little bit bigger, so the diameter is not quite 4, it's something like 3.8. And if you do 12 divided by pi, you're going to get something that's really close to 3.8. Let me actually do this on a calculator real quick to tell you what it is. 12 divided by pi gives me 3.8197 ... So you see that we are really, really close to being almost a perfect cube, only it's a cylinder. Okay?